Hey, Harsh here. Today we're going to talk about network latency, bandwidth, and throughput. Let's start with the definitions because they're often used interchangeably, but they shouldn't be. Latency is speed in terms of time. It is the time from the moment a request is sent until the response is received. It's measured in milliseconds mainly. Bandwidth is capacity, is the maximum width of the pipe. If you have a 1 gigabit connection, that is your bandwidth. Throughput is reality. It's how much data actually gets across. You might have 1 Gbps bandwidth, but if you have a packet loss, your throughput might only be 750 or 500 Mbps. Throughput can never exceed bandwidth, but it is almost always lower due to protocol overhead. Latency isn't just one number, it's the sum of four specific delays. First is the propagation delay. This is limited by the speed of light. In fiber, light travels about two-thirds the speed of light in a vacuum. Second, serialization delay. This is the time it takes to actually push the packet onto the wire. On a 1 Gbps link, a 1500 byte packet takes about 12 microseconds to serialize. On 100 megabytes per second link, it takes 120 microseconds. Higher bandwidth does reduce this specific component of latency. Third is processing, which is your router CPU logic. And fourth is queuing. If the router is congested, your packet just sits in a buffer. This causes jitter or variable latency. Let's look at hard physical limits. If you're building a real time trading app, this is your ceiling. A round trip between New York and London is roughly 5,600 kilometers. Even if you had a straight fiber cable with zero routers, the light takes about 28 milliseconds one way or 56 milliseconds round trip. In reality, internet isn't a straight line. You have multiple hops, zigzag routes, and repeater stations. So realistic ping is usually over 80, 100, 120 milliseconds. No amount of code optimization will fix this. The only solution is moving the data closer to the user. Often, to get high throughput, we must sacrifice latency. Think about batching. If you send data immediately, i.e., low latency, you have high protocol overhead per packet. If you wait to fill a buffer, which is batching, you send more efficient payloads, high throughput, but the first item in that batch had to wait, increasing its latency. We kind of see this in Kafka. You have to decide, do I want it fast or do I want the volume? TCP is connection oriented. Before we send a single byte of HTTP request, we have to talk. Client says sync, server says sync acknowledgement, client says acknowledgement. This is 1.5 round trips just to say hello. If your round trip to the server is 100 milliseconds, you have wasted 150 milliseconds before the user sees anything. If you add HTTPS, TLS, you could be adding even more round trips for your cryptographic handshake. This is why cold starts and serverless functions or new database connections are so expensive. The bandwidth delay product tells you how much data can sit in transit before the sender gets the acknowledgement back. If the TCP window size is smaller than the BDP, you cannot utilize your full bandwidth. You will stop sending and wait for an acknowledgement, leaving the bandwidth idle. If you are designing a file transfer system across continents, you must tune your TCP buffers to match the BDP, or you will be throughput bound by latency, not bandwidth. High throughput requires low packet loss. In TCP, if you lose a packet, the protocol interprets it as a congestion. It cuts your transmission speed in half, which is congestion control, and waits to retransmit. A 2% packet loss can kill your throughput by 90% on high latency links. Jitter is a type of variance. If the ping is 20 ms, then 100 ms, then 20 ms again, that's high jitter. This is a nightmare for voice over internet protocol and gaming because buffer runs dry, causing choppy audio. Averages hide problems. If your average is 100 milliseconds, but your P99 is 2 seconds, your system is slow. That P99 represents the tail latency often caused by garbage collection, resource contention, or a single slow microservice. At scale, P99 is what defines user reputation of your product. Always designed for tail latencies. We have talked about how latency is packet size divided by bandwidth. How do we shrink the packets? JSON is great for compatibility, but it is bloated. It repeats field names every time. Protobufs used in gRPC are binary. They compress that data into a tiny byte stream. For internal microservices, where you control both sides, switching to gRPC can drastically improve throughput and latency just by shrinking the data on the wire. Since we can't speed up light, we move the server. A CDN like Cloudflare or Akamai puts servers in thousands of cities. When a user in India requests a video, they don't hit your Virginia bucket, they hit a server in Mumbai. This cuts propagation delay from 200 ms to 10 ms. It also acts as a massive shield, absorbing traffic spikes so your core database doesn't melt down. Latency is also psychological. Optimistic UI is a design pattern where when a user likes a post, you turn the heart rate immediately using JavaScript even before the server confirms it. If your network request fails later, you revert it. This makes the perceived latency zero, even if the network latency is 200 ms. How do you debug, monitor, and observe these things? Using distributed tracing, tools like Jaeger, Datadog let you visualize the request lifecycle. You can see 20 milliseconds in load balancer, 115 application, and 500 in database. Without this breakdown, you're just guessing whether the problem is in network or your code. If you need real time, go to UDP or WebSockets. If you are global, CDN is mandatory. If you're throughput bound, batch your requests. If you are handshake bound, keep your connections alive. And always measure your tail latencies, not just your averages. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.